Welcome back. Hope everyone's doing okay. Had a good day today. The reason we pushed this over because I was closing on a house and done deal today. So I appreciate you guys, coming here for the late start. Had to go through a lot of hoops to get that house. But anyway, what we're going to do is continue with what we got going on here, which is chapter 6, and then definitely we're going to have time to finish that today and then jump into 7, continue. Next week, as a refresher, remember that there is exam number 2, which covers chapters 4, 5, and 6. Okay. So any questions before I begin? Any questions, comments, concerns? Yeah. All right. GT, I don't understand that one. Oh, good to go. All right.
Good to go.
All right. Sounds good. All right. Thank you. All right. So chapter 6. Now what this deals with is the periodic table. You got a whole chapter on the periodic table. Okay. And let me introduce you to this crazy looking character. Dmitry Mendeleev. Dmitry Mendeleev is responsible for the beginnings of the original periodic table. He arranged the table in the order of increasing mass. And what he did was he put the elements with similar properties in the same column. Okay, so, and the amazing aspect about this, given the time period, 1869, what they had was the power of observation and doing experimentation and observing. There wasn't a lot of, fancy equipment that we have to date. I'm thinking 100 years from now, when scientists look at our equipment, they're going to be like, wow, how'd they do that? So what he did, he created this periodic table. Okay. And he realized that some elements had very similar reactivities. Well, we've learned that within the group, specifically the A elements, that what they share is the number of valence electrons. Okay, so group 1 has all 1 valence electrons, group 2A, 2 valence electrons, etc. And being in the same group, because that's what they share, the number of electrons, they will react very similar. Okay. He also had like holes, in his periodic table where he predicted that there should be other elements, and that just started up a whole slew of research and developments to seek out these missing elements. And little by little, over the years, we ended up plugging the holes and kind of rearranging the periodic table into what we know it now. Okay, as we see it now. Now, there are other versions of the periodic table. I'll give you some examples, but this one here is probably the one that has hung, has remained. So, okay. So what he did, this scientist mostly, he put the periodic table in sequence of increasing atomic numbers, and this is what he came up with, this particular periodic table. So also we have what's called the periodic law. Elements in the same column have similar properties, and we know now why that's the case. Now this is really true only for to a large extent for the A elements. For the B elements, a little bit tougher to make that statement, but for the A elements, they all have similar properties and similar reactivities, the ones in the same group. Okay. Been a variety of different versions. Now the periodic table, if you notice the bottom 2 rows, they actually belong inside the D elements, where the D elements are. And if we were to take those 2 rows and put them back in, that is what the the periodic table will look like. It's been expanded. So the green ones, the green elements are those shown at the bottom of the periodic table as we see it here in this slide. Okay. But you know, it takes it, expands it, spreads it out, makes it a little bit more difficult to work with. So that's why they took the green elements out here, the inner transition metals. As we're going to learn, they have a very specific name. Okay. Another example of a periodic table has been the circular periodic tables. And they've been introduced with mixed results. You know, people still really don't care for this. And even more abstract is this type periodic table, which all of them have their plus and minuses, you know, of advantages, disadvantages of utilizing them and demonstrating how the periodic tables go. But in this particular one, there's a prediction, just like Mendeleev's original periodic table. There was a prediction in his case where there should be other elements. And if you look at here, what this does, this predicts a series of elements called superactinides. Okay. Well, obviously we haven't obtained those. They are looking at making more elements. The element number 118 is what we're up to now. And there are scientists right now to speak that are striving to create bigger elements. Okay. So let me see 1 second. I need to stop. There's a problem from my end, so bear with me for a second. There's something going on here on my end, so bear with me for a second. Zoom. Okay. And so Niels Bohr brought up the idea of electrons existing energy levels, and it kind of altered the periodic table shape a little bit. In other words, we took the F block, if you recall. The first two columns we designate those as the S block elements. The blue here, the inner elements designated as the D block, and then the P block, and then down in the bottom designated as the F block. And there are the corresponding orbitals for that particular energy level, okay, shown there. Okay, so the horizontal rows of a periodic table are called a period or an energy level. When we talk about electron configurations, we tend to use the term energy level, but when we're just using the periodic table as a guide or as an aid, we talk about a period, which are the horizontal. There's seven periods, okay? You heard me say the term group for the vertical column. These are called groups. Now, elements in the same group, as we stated earlier, exhibit similar properties because they share the same number of valence electrons. Now, the A, the ones with the Roman numeral A, are main group elements, okay? Whereas those with the B lettering, which are the D block, okay, are called, and the D block and the F block are called transition metals. So they all have their own specific name. The F block are going to be given a name, also have a name. They are transition metals, but they call them the inner transition metals. Okay, so we have the A group, then the B group, which are called transition metals, and then the F blocks are called inner transition metals. Okay. This is something we've already talked about at length. The period represents energy level and shell. Okay. And then this is a family or a group. Okay. They all exhibit the same chemical properties, again, because the number of valence electrons. Now, some of these elements in their group have their own little special name. Okay. Now, the ones in group 1A, excluding hydrogen, so that's why you see here that I did not talk about hydrogen and cover it up, because hydrogen is a gas and it's not a metal, right? So in group 1, their specific name are called the alkali metals. Okay. In fact, that's what they were called before they came up with the Roman numeral nomenclature. So the next one, the group 2, right here, are the alkaline earth metals. Okay. Now, way over in the far right, where you have group 7A, which consists of fluorine, bromine, chlorine, iodine, they have their own little name called halogens. Okay. You may have heard of them, the term halogen someplace before. We got halogen lamps, okay, using some of these very bright lights. And then finally, the last column, as we talked also about before, is the noble gases, called noble gases because they're very unreactive, okay? And they're very unreactive because from neon down, they have 8 electrons around the valence shell, the outermost shell. And helium has 2 electrons. It's fulfilled its duet rule. All the other ones have a octet rule that everybody's striving to do. Nonmetals strive to have an octet. Metals strive to have an octet. And they do that by either losing or gaining electrons. Okay. All right. So the D block, the ones in green, as I stated, they are transition metals. And they're very difficult to predict as far as what kind of charge they are. I can say the only thing you can predict at this point in time is the ones in green and the ones down in gray. And well, I guess it's that. Whatever color that is, I can't see it from my end. It looks like an orange color. The only thing you can predict is they will have a plus charge because they are metals. Remember, all metals lose electrons, and losing negativity, they become plus. And we cannot predict, like the other groups, that specific charge because there's examples, for example, iron. Elemental iron is a 0 charge. Iron has an equal number of protons. Here's iron right there, number 26. There's 26 protons, 26 electrons. But iron also has a capability of losing either 2 or 3 electrons, which results in forming 2 ions, different ions, iron 2 and iron 3, okay? And it depends on the reaction conditions. Copper, for example, we have regular copper, copper 0, but there are 2 ions of copper. It can lose 1 electron to give us +1, or it can lose 2 electrons, which gives us a +2. Totally different compounds. One results in a blue color, very beautiful blue color solution. The other one's more of a green color. Growing up in Superior, Arizona, it's a mining town. It's about an hour drive east of here. It's a copper mining town. I recall as a young kid playing in this lagoon. They had a very nice, beautiful blue color in some areas. And we thought that was cool, blue color like the ocean. Yeah, it turns out it is copper metal in there. And not the best thing to play with because too high a concentration of metals can cause a problem. Okay, so right there. Now the F block, there's two names. Okay, well, in general, all of them are called inner transition metals. The D blocks, the green ones here, are transition metals. Within the inner transition metals, there are 2 that have, each row has their own specific name. The top row, starting with number 58, are called the lanthanides right here. These are lanthanides that go from here all the way across to here, from 58 to 71. They're also called the rare earth metals. Very definitely are rare. A lot of them are used quite extensively in electronics, so they play a crucial role in electronics. And then the next row is called the actinide. actinides series. Okay? Literally all of them there are radioactive. Yeah, radioactive, except the number 1 here. But if you recall the atomic weight here in parentheses, when they're in parentheses tells you they are radioactive elements and not very stable to do a lot of analysis on them. Okay, with that information, we can answer the following questions. In that they might be asked, we need to identify the alkaline metal in the 3rd period. Okay, so we need to know what period we're talking about. So this is 1, 2, 3. Okay, and then the alkali will be the ones in the first group. So it's got to be sodium. And sure enough, it is. Okay. The halogen, which we know is the ones in group 7, where the fluorine, chlorine, bromine, and iodine are at in the 2nd period. So, this is 1, this is 2, right? This must be fluorine. Okay. Notice I said the term fluorine. That is the element, fluorine. If I would have said fluoride, that would be the ion, okay, with the negative charge. And then finally, the noble gas, which brings us to the last column, column 8A, in the 4th period. So 1, 2, 3, 4. It must be number 36, which is Kr, aka krypton. Krypton, okay, krypton gas. All right, so here by utilizing the period they're in and the name of that particular group, we are able to identify the element that the question is asking us. Okay. Now, excuse me, refresh your memory as to metals, non-metals, okay? Not so much a metalloid, just be aware that they're here, obviously, and how do we know which ones? Well, the metalloids are right here in green, okay? Those are the metalloids. Everybody to the right of the metalloids that means everybody over here, are non-metals, including hydrogen, okay? And that means that everybody else over here are metals. Now we need to be able to identify metals and non-metals, because what we're going to learn is when we take these elements and create ions by either losing or gaining electrons, they form ions. We can start putting together the metal and the non-metal. When we create a metal and a non-metal, we have what is called an ionic compound, ionic, okay? So between a metal and a non-metal combination, good example would be sodium chloride, good old-fashioned table salt. Notice here's sodium right here, and the chloride's right here. Sodium is a metal, chloride's a non-metal. That creates what is called an ionic bond, which in turn makes an ionic compound, CPD, a shorthand for compound, okay? And so by looking at the formula, realizing that you're dealing with a metal and non-metal tells you have an ionic compound, which then tells us a lot more properties down the road here, okay? Whether it's soluble in what things it's soluble in, okay? Things like its physical properties. Ionic compounds tend to have a very high melting point, not very easily melted, okay? Totally different properties. Now, the other combination, let me clear this off, is when you have a combination of non-metal combining with another non-metal. Okay, And that could be the simplest example would be H2O. H2O, water. Hydrogen is a nonmetal. Oxygen is a nonmetal. What that tells you is this water is not an ionic compound because there's no salt in its structure. This one is called a covalent bond / which makes a covalent compound. Okay. And the main difference, you see, the next chapter deals with bonding and compounds. The main difference of all the chemicals out there in the world, we only got two types, ionic and covalent. And the main difference between the two is two things. For the ionic, it's a metal and non-metal. And when they come together, they each have a full positive or a full negative charge. And when they come together, think of those. An ionic compound is two magnets coming together and attaching themselves because of the full plus and full negative charge. And they never share anything. They're just attracted to each other because of the nature of the beast, the positive and the negative. When it comes to covalent compounds, they literally make a bond where they share. Ionic compounds, let's say my fingers represent 2 electrons, well, 2 ionic compounds, I should say, positive and negative. They just come together and touch each other in the fingertips and attract each other like 2 magnets. Covalent compounds, here are 2 compounds bringing in their valence electrons. They literally make a bond and they share a bond with each other. And we're going to learn there's equal sharing and unequal sharing, which tells us a bunch of other things with respect to properties and reactivity. Okay, so those are the 2 main compounds. And to be able to identify which type you're dealing with, you need to know if you're dealing with a metal and a non-metal. You need to identify the metal and the non-metals. Okay. All right, so refresh that particular diagram. All right, well, atomic size. Basically, it is the distance between the nucleus and the outermost shell, the outermost electrons, okay? Depending on the size, we can have a small atom or a large one. But you already have, okay. Let me get this phone. One moment, please. I needed to answer that. Okay. Yeah, there's only 2 of you here, so plus myself. I see the question. Anyone else here? I did have, yeah, Zaya and Max. All right. So atomic radius. Okay, that's basically the distance between the nucleus and the outermost electron. Okay, and you already probably have one trend that you can deduce simply by looking at the periodic table, that we know going down the periodic table, we are increasing the energy levels 1 through 7. So it stands to reason that the elements in period 1 are going to be much smaller than the elements of, say, period 7. Okay, so the trend is going down the periodic table. The elements get bigger. Okay. Increases as we go down the column. Okay. Now, where the trend kind of changes a little bit here, when we go from either right to left, however you want to look at this, tomato, tomato, I look at it from left to right, just because that's the way I read, okay? In that, when you go from left to right within the period, what tends to happen is the radius of the element gets smaller. So let's bring back the periodic table. So that means that if I compare let me see, let's just say sodium to chlorine, which is way, okay, they're all in the same period, but here's sodium number 11 and chlorine being number 17. They're both in the same period, number 3, but when we look at the radius, sodium is much bigger than chlorine. And you might ask, well, why is that? Well, let's think about it for a second. Sodium on one side, on the far left side, has 11 protons and 11 electrons, okay? Whereas chlorine over here has 17 protons and 17 electrons, okay? And so obviously, there are 6 more protons and electrons for chlorine, which actually puts more of a nuclear force. There's more positive, more negative. And what's happening, the result is like getting 11 magnets, if you will, compared to 17 magnets, and that force gets stronger. The result is the nucleus, the positive protons tend to pull the electrons closer in, reducing the radius of the atom, okay? Because as we go from left to right, we increase the positives, protons, and negative electrons. We increase the nuclear charge of the element, and therefore we get a smaller element. Okay, now, and here is, so going from left to right, as positive charges increase, the electrons are pulled down closer, so the atom actually gets smaller within the same period going from left to right. Okay, and one way to look at it is the snowman, where the 3 segments of the snowman represent the radius. Obviously, we're up on the top. The head represents maybe period 1, you know, and as we go down the period, this is number 1, second period, third period. Obviously, the radius increases as you go down the periodic table. So take that same snowman and just flip it over, and now you are within the same period, whichever period you select, and the radius gets smaller. It goes from the far left, okay, to the far right. The radius gets smaller. But there's an additional explanation too. Yes, we get more positives, electrons get pulled down. But the other aspect is this: because of that effect, you know, we know that metals want to lose electrons. Okay, very readily want to lose electrons, so they have a tendency not to, because the electrons, the valence electrons, is way out there all by itself. Okay, and on the far right, metals want to lose electrons, non-metals want to gain electrons because they hold on to their electrons even tighter because the positive charge has increased. So they're holding on to it much tighter. It's not going to give up its electrons as readily as the metals will do. So there's one particular trend as follows. Excuse me. Now there's a diagram kind of to give you an idea of the relative size as we go across the periodic table. Yes, there's some areas that looks like they're about the same, and that's okay. But really, it's really in the big elements down in this region in here. Doesn't look like there's much of a change, and there's somewhat, basically a little bit. And as drastic as up here where we're dealing with the smaller, a little bit smaller elements. But the trend you can see, it gets smaller as you go across and get bigger as you go down with respect to the radius. Okay. Now you might be asked a question. All right, I got 3 elements here. Which one is larger? Well, to answer that question, you have to identify them on the periodic table. And so I got a diagram here that shows you these three within the periodic table and note they are group 6 elements. They're all within the same group, which means that as you go down, they get bigger because you're simply going into a higher energy level. Okay, so there's more energy levels, thus a bigger radius. Now, the second example, magnesium, silicon, and sulfur, to answer this question, also identifying the periodic table and see where they are relative to each other. You can see that they are, magnesium is in the far left, and then you got sulfur way over to the right, okay? And so the trend here is that magnesium is bigger with far as radius, and sulfur is smaller because it has more protons and pulling the electrons closer into itself. All right, so now on the course website, there's other YouTube videos written by Dr. Kim concerning this topic, atomic size and so forth. So yeah, get a chance to go ahead and listen to them to help you out with some more information. Okay. Now, this idea of protons and electrons and the radius are all tied in when you think about it to a physical property of each element. But it stands to reason, if you give it some thought, that if I hold on to my electrons loosely compared to another element that's holding on to them tighter, thus making the radius get smaller, it seems that it would be more difficult from an energy perspective to remove an electron from that element that's holding on to its electrons very tightly. And that we're going to learn here is correct, is true, because we have what is called the IE, or ionization energy. Now, what's important here is not to confuse the IE property with the next property we're going to talk about called the EN, electronegativity. Totally different. We're going to use the next property quite a bit. This is just trying to explain how much energy it takes to remove an electron. So you can make some predictions here if you think about it. Okay, you can make some predictions and say, okay, well, if I'm comparing metals and non-metals, I can probably predict that the ionization energy to remove an electron, well, let me define what ionization energy is first. Sorry about that. It is the amount of energy necessary to remove an electron from a neutral atom, which is an element. So taking that sodium element and hitting it with energy to kick off that electron, okay? Kick off an electron. It measures that amount of energy. And so, as I was saying, if we understand now that metals want to lose electrons, and so they already have the property of losing electrons when we compare them to non-metals that want to gain electrons, well, you can predict and say, well, you know, metals are going to take lower amount of energy because they want to give them up anyway, compared to non-metals that want to hold on to electrons, okay? And then you might say, well, what about within metals? Well, look at the size of them, okay? If they're down in the same group, and we know that the one in the bottom is bigger, and that means their valence electrons are further away from the nucleus. Think about this. If I have, let's say here's my, here's my nucleus of one element, and my electron is maybe right here, one electron, okay? An X amount of distance, whatever it may be. I'm obviously not drawing it to sketch to the correct size. But then I got another metal that its electron is like way out here, okay? Further away from the nucleus. Now, it stands to reason, if you give it some thought, that the interaction between the electron and the nucleus is, and this we'll call this A and we'll call this B, is stronger for A than it is for B, simply because that electron is closer to the nucleus, okay? In B, the nucleus is further away. So this interaction between the center, the nucleus, and the electron will be much less. So I could predict that when it comes to this IE, ionization energy, that it's going to take more energy, more IE here to remove an electron than it would from the one that's bigger, okay? Simply because its electrons are further away and it's held on loose, much more loose than A is. All right. So as we go up a group or down a group, it's easier, whichever way you want to look at it. As we increase, it increases as you go up a group, makes sense, or it gets less as you go down a group. Again, for that reason, is because those electrons down the group are those electrons that are coming from a bigger element. So the interaction between the nucleus and that electron is much less than one that is smaller, okay? And if we look at going from left to right, the IE increases. Well, the same reason the radius increases is the same reason it decreases, I should say, the same as we go across the period. As we go across the period, what's happening? We've got more protons, more electrons. Those electrons are pulled in closer. Just makes sense that the ionization would be much greater for those on the far right of the periodic table compared to left within the same period. Okay. And also on top of that, back to the old adage, metals want to lose electrons, non-metals want to gain electrons. So they're not going to give that one electron, give it up very well. I forgot to mention here the type of reaction. This is a process, either physical or chemical. I know that because I got an arrow that tells me something's happening to my reactant, which is the sodium. And on the right of the arrow are my products, whatever they may be. In this case, I'm knocking off an electron from the sodium element, and I'm creating one electron, that's my plus. And then I got, because sodium lost an electron, it's gonna now has a +1 charge, okay? This diagram demonstrates that energy as we go across, IE energy as you go across the periodic table. You can see this position. Let me change the color so we can. This position right here, that's hydrogen. Okay, so in the periodic table, far left table, go all the way across, we go to helium, which is right here. Now note, hydrogen has an IE energy, I don't know, about 14 units or so. And as it shoots across to helium, this thing kicks up to almost 24 units of energy. It takes more energy to remove an electron from helium than it does from hydrogen. And it stands to reason because helium now, its duet is full. It's holding on to those electrons as tight as they can be. It's not going to give them up very readily. Now, once we get a helium, go around the periodic table, and we end up right here. This is lithium. Okay, so that's going, we flip the wire. We are now in the second period. This is the first period. This is the second period. This is the third period. And this is the fourth period. So we're in the second period. We start off with lithium in the far left. It is a metal. It's going to have the amount of energy to remove electrons somewhere in the order of 6 energy units, right? So as we progress across the periodic table of the second period, we end up in the far right, which is neon. And its energy is somewhere around 22 units of energy, whereas lithium was about, what we said, about 6. So there's quite an increase of energy necessary, ionization energy necessary to remove an electron. Now, as we go around the horn, we end up with sodium right here. Got sodium here, and we go across the periodic table, and we end up with argon, okay? Similar trend. Now notice that it's not absolute values, are the ones that are noble gases on top. Its energy is getting less and less. Helium had required the most amount of energy, and then neon, and then argon, and so on and so forth, okay? And it looks like now the slope of that line within each group is getting straighter and flatter. It's, you know, starting about an exponential increase, and then slowly as you go down the period, that slope, though it does increase from left to right, and that is drastic. And it's simply because we're going to reach a point where it's going to be like no little difference. Because by then, all electrons, all of the billions of electrons are way out there, out to the neutrons. So there's not a lot of strong interaction between the nucleus and the outermost electrons of the big elements, okay? All right, so let's clear this up. Okay, question here, we say, which has a larger IE and why? And we have chlorine, aluminum, and magnesium. Now, you don't even need the periodic table here. Could I answer this question when I'm given this choice of these three elements without looking at the periodic table? Okay. Is there anything about those three elements that I can see and very quickly say, oh, of course, one of these is going to have a higher ionization than? Anybody have an idea? Okay. Hello? Oh, Maya, are you here? Can the three of you hear me? I just look at the note here. If someone asked the question, anybody here?
Yeah, I can hear you.
Okay, I thought maybe
I'm trying to figure it out still.
Okay. I just gonna make sure that I maybe didn't lose contact here. All right, well, tell you what, look at these three and then ask yourself the question, of those three, is there any difference between these three? And the answer is yes. Okay, yes, obviously there are three different elements, yes. But what type of elements? There's only three types of elements. We have metals, nonmetals, and metalloids. We're not gonna work a lot with metalloids. Yeah, at least not at this Chem 130 level. But we're gonna work a lot with metals and nonmetals. And if I look,
Chlorine?
Chlorine, exactly. Chlorine is a nonmetal. And that tells you just by nature of the beast, chlorine is a nonmetal. It wants to hold on to those electrons like crazy because it's close to getting that octet. And it wants to gain electrons, okay? So, and when I compare them with aluminum and magnesium, who are metals that just by nature of their beast, they want to give it up. So I can predict very quickly without even using the periodic table that chlorine would have a higher ionization energy. Okay, and if you don't see that, well, we look at the periodic table. I've isolated the three of them, okay? And remember that the trend for the radius was from left to right, it gets small. So chlorine has a smaller radius compared to the other two in here, aluminum and magnesium. And that is because chlorine has more positive and more negative forces. It has more protons, more electrons, and they tend to pull, the positive protons tend to pull those electrons in, making chlorine smaller compared to the others. And also a side result of that is if I try to take off one electron, it's going to happen, but it's going to take a lot of energy, okay? And so chlorine would have the higher IE, okay, because one answer would be it's a nonmetal and it wants to gain electrons, and another answer would be it has more protons, more electrons, the nuclear force is stronger and it's going to hold on to its electrons much tighter than aluminum and magnesium. Now, in this case, we're going down the periodic table. And so now we're looking, they're all metals. So distinguishing between metal and non-metal won't help us here because everybody's a metal here. But what they have in common, they are all in group 1A. And what the other thing they have in common, they all have one valence electron. However, you're going to see going down the periodic table that this one is much bigger. And so let's say just for not to scale, but here's my nucleus, all three of them. And my electron for lithium maybe will be about right here. My electron for sodium, maybe it's a little bit further away. That's supposed to be an electron charge. And for RB, maybe way over here, okay? That's supposed to be electrons in the interaction with the proton. And you can see that the last one here, its electron is further away from the nucleus, so there's going to be less interaction with the nucleus. And the one on top, that electron is much closer to the nucleus, and therefore it's going to hold on to that electron much tighter. Lithium will than RB would do. Okay. Just because it's smaller and the electron's a little bit closer. Okay. Again, there's a video on ionization energy. Take a look at it and help you out with more information. Okay, which now brings us to electronegativity. Now this property, now here prior to this, ionization energy deals with the amount of energy necessary to remove an electron from an element, a single element. In the case of electronegativity, now we are talking about bonded electrons, okay? And this property will affect a lot of things about a chemical compound. Because as I stated earlier, when I said there's a covalent bond where electrons essentially are being shared, if you will, between two elements, there is two types of sharing. There's equal sharing and unequal sharing. It's like a tug of war. You know, when there's equal sharing, both of the elements involved are the same everything. So there's an equal sharing there. That results in certain properties for those type of compounds. When there is unequal sharing, it's like a tug of war between, say, a 200-pounder and a 400-pounder. They're pulling on a rope. Well, obviously, the 400-pounder, just by virtue of mass and ability, is going to pull that rope over to itself. And that's what happens here, that between two different elements bonded, the one with the higher electronegativity is going to pull the electrons toward it, which results in a bond with a specific property. Okay. All right. Now, of all the elements there, fluorine has the clear this, change this a little bit. Fluorine, which is about right here in the periodic table, okay, is the element with the highest electronegativity. And so we use fluorine as our benchmark when we are comparing the electronegativity of different elements. For example, carbon may be about right here, nitrogen's about right there, okay? And if we want to know which one of the questions asked, well, who is more electronegative, carbon or nitrogen? Well, we take the periodic table, find the position of those elements, carbon and nitrogen, and determine who's closer to fluorine. And in this example, nitrogen is much closer to fluorine. Therefore, the electronegativity of nitrogen is much greater than carbon, which then creates a certain property if carbon and nitrogen are bonded to each other, okay? But we use fluorine as our benchmark, if you will. And from that, because, you know, electronegativity, there are absolute values of electronegativity for all the elements. And it's not necessary to memorize or learn all those numbers. And some people do, and that's fine, but we don't need to do that here for Chem 130. All we need to know is which one is more electronegative based on their position relative to fluorine, because we know that fluorine is the most electronegative. So the trend is from left to right increases, and from bottom to top, it increases, going all to fluorine. Obviously, noble gases do not have any electronegativity. Okay, they don't form bonds. And for Chem 130, I can say that they don't form bonds, you know, but in advanced classes, we'll find that the bigger elements. Remember I said earlier when we were looking at that table of those electrons further away from the nucleus, the electronegativity the slope of the hill went like this, down like this, because those electrons are far away from the nucleus, and they're not interacting with the nucleus as much, so they have a possibility of forming compounds. But we're not gonna go there. We just say noble gases, they won't do anything. All right, which brings us to the end of chapter 6. See how quick that was? Yeah. Any questions? Yeah. All right. Well, let us continue with chapter 7. Let me wet the whistle here a little bit. Okay. Chemical bonding. I kind of introduced it a little bit earlier in the first chapter. Now I tend to do that when I talk a particular chapter. When I can, I try to introduce material that we're going to see the next one. And I do that because I want a gradual progression. I want you to grasp the concept, because all these things are going to be brought together. You know, we so far we talked about the elements. Okay, we talked about how the electrons are, their electron configuration. Okay, we talked about who loses electrons, who gains electrons to form ions. Because the next step is, once we understand that who forms positive ions and negative ions, we're going to start bringing those positive and negative ions together to form a compound. Once we get those compounds put together, we're going to start reacting them with other compounds to form products, okay, with their chemical formula. So everything, hopefully I've tried to tie it all together. At the end, we're going to bring it all together. Don't forget about the electronegativity, because it comes time again back to us about electronegativity. And that's the affinity of an atom that is bonded. That's the difference. That is bonded. It has the ability of an atom to pull electrons toward itself. Okay. And if they pull it more than the other atom, we form a particular type of bond. There's two types of bonds. I mentioned that: ionic bond and covalent bond. Okay. Now I can kind of put it all together a little bit to begin with, because with this, we're going to learn about chemical bonding, and then we're going to learn about formulas and how to make formulas. Okay. And so we have ionic, I brighten it up a little bit here. We have ionic bonding, which is a non-metal bonded to a metal. Okay, and then we're going to have covalent. Note the term covalent, valent coming from valence electrons, co, where they're sharing valence electrons. So covalent, we're going to have, and that is a combination of a non-metal, Nm, and a non-metal. Okay, so within the covalent, we have two subcategories, which is related to the electronegativity. When the electronegativity of these two atoms are the same, we have what's called a non-polar bond. You know, polar, what does that mean? Well, water is very polar, and we're going to learn why it is. But there's a pole around us. A battery is a pole. The moon, excuse me, yeah, the moon is, but the earth is a pole. North pole, south pole. A battery has a pole, positive and negative side. It forms a differential, if you will, a gradient. It is a pole. Well, when the two atoms are the same, there's an equal pull. The electronegativity is the same. We end up with, which is called the nonpolar. When the pull is different, because the electronegativity is different, I should say, we have a polar covalent bond. Best way to describe this is to say oil, like regular vegetable oil, is made up of nonpolar bonds, okay? Whereas water is made up of polar bonds. The other aspect about that is, from a physical perspective, nonpolar species will dissolve in nonpolar species, whereas nonpolar species will not dissolve in polar species. We know, if you like Italian dressing, if you've ever seen a bottle of Italian dressing, you got two layers, oil layer and the water layer, polar layer and a nonpolar. And all that's related to the type of bond the chemical in that Italian dressing has, okay? And it's related to a non-metal and a non-metal combination, and as to whether one is more electronegative than the other. But we'll get to that. So if you haven't done so, okay, do download the shapes table, and let me go to the shapes table here, because we will utilize this. In the shapes table, there is a table. Okay, there's information up here, but in this table, this deals with molecular shapes and bond angles. Okay, so we're going to take the valence electrons of a compound. We're going to look at all the elements of a compound that are involved in whatever compound we're given. We're going to determine the number of valence electrons each compound brings to the table. We're going to tally them up, okay? We're going to divide by 2, because we know that every single bond has 2 electrons, so that tells me how many bonds I have to work with. Then I'm going to start connecting. We're going to be given the central atom and then connecting all the other atoms, okay? Until such time that all the electrons around each element has 8 electrons. They're going to be shared, for example, but you got 8 of them. Once we do that, from that, we create what's called a general formula. Okay? I'm giving you the rundown here, in short rundown of what we're going to be doing. We end up with a general formula, like AB3. It's not a specific formula, it's a general formula based on the structure you come up with. A represents what is called the central atom. A is the central atom. Every structure, every formula that we give you, you're going to be told who's the central atom. That's the central atom, whatever the case may be. For example, this species CH4, it's called methane. Carbon is the central atom. So carbon is in the middle, and the hydrogens, 4 of them, are bonded to the carbon. So that's the central atom. And in this general formula, A is always 1. Okay, it's a given. A, we're only going to deal with 1 central atom. B represents the number of elements bonded to the central atom. So in this case, the example I give you here, I got A, B, and then 4, because there are 4 hydrogens bonded to the central atom. The B doesn't have to be the same. The elements do not have to be the same. It could be different, okay? So that's what the subscript is here, the 2 subscript, the 3 subscript. Now, there are examples where we have E, So in this case, E represents the number of what are called lone pair electrons. If we look at the structure here, we have two dots that represents a lone pair electrons on the central atom. Not all electrons have to be bonded to something else. There can be electrons, a pair of electrons on an atom and just not bonded to anything, okay? We call those the lone pair of electrons. They're not doing anything and they're sitting on the central atom. So we need to count if we have any lone pair of electrons in the central atom. Not the other atoms, but in the central atom. So after all said, everything said and done, we have these general formulas, okay, AB2E, etc. What that does now, once we know the general formula, now we know what's called the molecular geometry. What is the geometry of that compound? Okay, and here's the shape, how it looks like. And that geometry has a specific name. And this one's called linear for the first example, AB2. We got trigonoplanar for AB3. The most common one in nature is tetrahedral, where you can see we got the central atom here, and then we got four moieties bonded around the central atom. Remember that each line here represents a bond of 2 electrons. That's a bond. We draw a line to represent a bond between 2 elements. We can put 2 dots, but that's a lot of dots we got to work with. So we just simply put a single line for a single bond, because we have 3 types. Single, if it's a double line, that's a double bond. If it's 3 lines, that's triple. And that's it. We don't have any more other types. It's either single, double, or triple. Okay? We don't have any quadruple. And each line represents 2 electrons. Okay? So these lines here represent 2 electrons, and them being negative, you know, if these were on the spring, you know, they're going to bounce around, but because they're negative, they're going to put themselves in a position where they have the least interaction with each other. And that's what that is, the tetrahedral. All the electrons are being pushed away from each other, and that's what you end up with this structure. So from that, molecular formula, we know the shape, and then we have what's called the bond angle, and that is the bond angle that's shown here between the central atom and 2 of whatever is bonded to it. In this case, the most common angle found out there is 109.5 degrees. Now, it gets less sometimes depending on what is bonded to the central atom. Whenever there are lone pairs bonded to the central atom, what that tends to do, because lone pairs tend to take up more space, they tend to shrink the bond angle. Hence, for trigonopyramid, that bond angle is not the expected 109.5, but rather less than 109.5 because of the lone pair in here. Same is true for this particular one. Okay, so we're going to, you know, it's a lot of information now, but we're going to go specifically a step systematic approach to this and how to break it down in steps so we can go through all that and actually start writing, determining the structure. Now, what information is that going to give us? Once we know the structure and how it is put together 3-dimensionally, the next thing we know we need to learn is, does it have polar bonds? Okay, and by looking at the structure based on the molecular geometry and knowing the electronegativity of the central atom versus what is bonded to, we can determine whether we have a bond angle, a polar bond. And if these polar bonds don't cancel each other out, we end up with a polar molecule. But if they do cancel out, we end up with a non-polar molecule, which gives us a whole slew of different properties. Eventually, we're going to get toward the latter part to a section called intermolecular forces, IMF. And the way we determine what type of intermolecular forces is determined by whether the molecule is polar or nonpolar. And whether it's polar or nonpolar, we have to go through the step to determine that, okay? And in these intermolecular forces would help us determine and compare and contrast two different compounds and say, okay, compound A is going to boil at a higher temperature than compound B. We can't do absolute comparisons, but we can do relative comparisons. Okay. And it's all based on electrons and the interaction with each other. Okay, so do take that out and print that if you haven't, so you can be aware of that particular table and be familiar with it. Okay. As stated again, it's over and over again, the goal here is to obtain 8 valence electrons around the atoms, with the exception of helium. Now, hydrogen, when we compare count the number of electrons around hydrogen, when it's bonded to something, it will only need 2, okay? It has a duet rule. Okay. Everybody else, all the other elements have to have 8 electrons around. We know about this. Metals lose electrons and become, if I did mention before, they have their own little name called cations. Ions is the generic term to describe both negative and positive ions, but specifically, cations are those metals that lost electrons, whereas anions are those nonmetals that gain electrons, okay? Cations and anions. Now, an ionic bond is what I spoke about earlier, and it's a combination of a metal and a nonmetal. So again, we go to the periodic table and make sure you understand who's a metal, who's not, and who's a nonmetal. Okay, in ionic bonds, the bond they make, which is really they should give it a different name, but it's considered a bond because a bond really is a sharing of electrons. Here, ionic compounds, ionic bonds are not shared. They're just attracted to each other because of their mutual charge, okay? And when we do this, always remember, we don't put together 2 positives, but we need a positive and a negative. Therefore, who makes a good partner for calcium ion? It would be the bromide, okay? The bromide, not the lithium. You won't see a compound with calcium and lithium together. Some examples of ionic compounds, I mentioned sodium chloride, but it can be potassium chloride. It could be any metal that you're working with. It could be any of the ones we have here. Calcium chlorides, calcium bromide. All those are ionic compounds because combination of metal and nonmetal. Okay, nonmetals are a combination of, covalent compounds are combination of metal and nonmetal. So some examples of that would be like hydrogen, all the diatomics. All the diatomics, they form a bond of 2 of the same elements. Okay, that's a covalent bond. Other examples, as I stated, was H2O and things like carbon dioxide and so forth. Okay, because there's no metals in there. Okay. All right, now, why is the formula calcium Br2? Well, let's break it down. When we look at calcium ion, we write calcium here, and we know it's going to become ionic. The ionic form of calcium will have a +2 charge. Now, how do we know that? Well, calcium is a group 2 metal, which means that there are 2 valence electrons for calcium, elemental calcium. So that tells you that it will lose 2 electrons to create the calcium +2 charge. Okay? The bromide, well, the halogen here, bromine, what it does is it is a group 7 element. Group 7 element, non-metal, tells me it's going to gain electrons, being a non-metal. And the number it's going to gain depends on what group it's in. being in group 7 and striving for 8, it's going to only gain 1 electron, okay, resulting in a -1 charge. If we're going to put these together, the thing to remember is this. We have to add enough, the number of cations plus the number of anions must equal 0, okay? So I need to put enough bromides together with the calcium ion such that they cancel each other out. Well, we know that based on this information, we know that we have to put 2 bromides together for every calcium. The 2 I put in front of bromide eventually becomes the subscript. So to write the formula for calcium bromide would be CaBr2, okay? Calcium bromide. Notice I didn't say calcium dibromide. And that brings us to nomenclature, which we're going to be doing not only the next chapter after this maybe, but for sure the nomenclature test that you need to pass to within 80% to get credit for it. But we need to learn how to name these compounds. And since I said calcium bromide and not calcium dibromide, it is because ionic compounds do not have prefixes in their name. Okay, it's just calcium bromide. Unlike covalent compounds, where we had CO2, guess what? Carbon dioxide as the prefix. Okay, so covalent compounds use prefixes. Ionic compounds do not. Okay. Unfortunately, if you look at some of the labels out there, and you know, I'm always reading the labels to see what kind of chemicals are in there, you'll see, I don't know what it is, a marketing thing or something, but they put in there the prefixes for ionic compounds. This has been set by the international organization that is in charge of naming chemical compounds. Every chemical compound has a specific name that the world has agreed to, all right? And that's because at one time, what was named, whatever it was in one country was different in another country, and there was a lot of conflict and ambiguity. So all that was cut out. Everybody's on the same page. Or in one of these things on this page is ionic compounds, no prefixes. Covalent compounds, yes. Okay. All right, so let me clear this up, and that is why calcium is a good partner with why there are 2 bromides for every calcium. Okay. All right. So it has happened in the past. I don't know why, but students, and I can understand why, but students read this formula and think it is diatomic bromine. Well, if it were by itself, that would be correct, okay? But there's a calcium in front of it. So already it tells you that calcium is the central atom here. Generally, when the first name is given, that tends to be 99% of the time the central atom. That means that everybody else is bonded to the central atom. Okay. And so if you see what you're thinking it's a diatomic bromine, make sure there's not a metal sitting there in front of it, because this is the format for writing calcium bromide. It's not calcium bromine. Notice the name, bromine versus bromide. All right, so this question says, which compounds are ionic? Okay, so by definition, to be ionic, you have to have a metal and a non-metal combination. Okay, all right. So let's look at the choices. We got KBr, which by the way is called potassium bromide. Okay, potassium bromide. So potassium definitely is a metal. And bromide's a nonmetal. So definitely that is a ionic compound. The next one is called sulfur. Okay, sulfur, because it's the first one written, and that's going to be the central atom. Trioxide. Okay, now how do I know that? Okay, point number one. Sulfur and oxygen are both nonmetals. So that tells me I have a covalent compound. That also tells me that I need to use prefixes. Okay. So this is sulfur trioxide. If you ever got behind a car real close and have an exhaust and it smells like kind of a rotten egg smell, nasty smell, that's probably what you're smelling. Okay, sulfur trioxide. HCl is what's running around. With the formula again. There's two names here. When it is simply, say, the gas form is called hydrogen chloride. Could be a little bit confusing, okay? If it's dissolved in water, it's called hydrochloric acid. You know, so that would be like aqueous. So the first example would be if it was in the gas phase, and we use, if this was AQ, then its name would be hydrochloric acid. Now, in the nomenclature, it pops up a lot, you know, HBr, HCl. Be aware if they're asking you, they're telling you just aqueous or not, okay? Because there's a difference in naming. All right, so again, both of these are non-metals, so they're covalent, so that can happen. So as far as being ionic. Next one is bromine, specifically diatomic bromine. Okay, now we don't, for diatomics, we just say bromine. I know earlier I told you use prefixes, but only when those elements are bonded to a different element that are covalent. When all the diatomics, it's just simply bromine, okay, no prefix. It wouldn't be dibromine, just bromine, just like chlorine, like iodine, okay? So bromine is a nonmetal, so obviously that's not ionic. Then we have carbon and oxygen. When it becomes bonded either through ionic compound or through covalent compound, the oxygen, its name gets converted to oxide, okay? And since we have two nonmetals, we got to use prefixes. So this becomes dioxide, carbon dioxide, versus this one, which would be carbon monoxide. Okay, notice the prefix. Again, both of them are nonmetals, therefore not ionic. And then finally, we have Mg, which automatically tells you I have a metal. And then chlorine, which is chloride, this becomes magnesium chloride, not magnesium dichloride, just magnesium chloride. It is not dichloride because it's ionic, and being ionic, no prefixes. Okay. All right. Those are the only two. All right, now what is going on with respect to ionic bonds? Well, let's take a look at this example here, where you have a combination of a nitrogen atom and a chlorine atom that combine to form sodium chloride, which is an ionic compound because you have sodium and chloride, okay? And this kind of diagram kind of represents, notice that the bond in there, the interaction right here. Okay, there's no sharing, it's just on the surface. We got a positive charge of the sodium, net positive, negative on the chloride. They come together and attract each other like two magnets. There's no overlap here of anything. So that's one aspect to see. The other aspect is this. Look at the relative radius of the sodium atom. Go from here to here, this is radius. And then look at it after it becomes ionic. Definitely got smaller. So the radius of the element on losing electrons gets smaller because the outermost shell is gone. There's no electron in there, they gave it up. So the next full shell is the next one in, and that's full, so it becomes smaller in diameter, in radius, excuse me. If we look at the nonmetal, here's the radius, and boom, it just blows up when it becomes the ion. Simply again, because this ion, the chloride atom, has enough electrons, it needs one electron, so there's space for one electron. And then adding one more electron to the p orbital gives you a p6 orbital. It takes up more space because it added more negativity into the outermost shell. So the radius gets bigger. So bottom line is this: the atom of the cation, is smaller than the atom itself. Okay. Here's the cation for sodium. It's smaller than the element itself. Whereas on the contrary, the ion for the nonmetal is bigger when it gains an electron than the element itself. Note this changes. Now let's consider the magnesium and sodium atoms. Okay, we know that magnesium has 12 protons, okay, and 12 electrons. It is in group 2 element. Okay, being a group 2A element, it has 2 valence electrons, and it's a metal, so it's going to lose those 2 valence electrons. So when it does that, now it has 12 protons and 10 electrons. Okay, so it ends up with a negative +3 charge. Sulfur, on the other hand, starts off with 16 protons and 16 electrons with a net 0 charge. It is a nonmetal. It has room for 2 electrons because it's in group 6. So 2 electrons. So now it still has 16 protons, but now it's picked up 18 electrons. Okay. So those are the corresponding ions for those respective elements. And then we can put them together on the 1-to-1 basis. Why? Because I got a +2 from magnesium, a -2 from sulfide. And so its formula would be MgS, and that's it. Okay. And they end up making an ionic bond. Okay, to recap, basically what I just stated about the cations losing electrons, and so the orbits are pulled closer, okay? And anions are the contrary. Now, true or false statement? It says here, the aluminum atom loses electrons, whereas the iodine atom gains electrons. What do you guys think? What do you think?
It's true.
It's a true statement, yes, because aluminum is a metal, whereas iodine is a nonmetal. Okay, and so true statement here. The aluminum atom is larger in radius than the aluminum ion. So would that be a true statement? or possible? What do you think? So the aluminum atom is larger in radius than the aluminum ion. Think about what happened to aluminum. Did it lose electrons? Yes, it did. So what do you think is happening to its radius as an ion?
It gets smaller, so it's true.
That is a true statement. That is correct. It lost the outermost shell. Next one is full. So it gets smaller. Now, the iodine atom is smaller in radius than the iodide ion. And that is also a true statement. Okay. And then finally, the aluminum and the iodide ions form a bond by attraction, and that is true. I did mention this, I'll state it now, but specifically, it is called an electrostatic attraction. Okay, electrostatic attraction. Basically, like two magnets coming together because they got a positive and a negative. Now here, remember another difference between the negative, the covalent bonds that we've been talking about and the ionic bonds, okay? In ionic bonds, we got a full-fledged positive and a full-fledged negative, for example, sodium chloride. With respect to covalent bonds, when there is a difference in polarity, difference in electronegativity in that bond, it forms a polar bond. And so now we start talking about partial positive and partial negative sides within that compound. Not a full-fledged, but just a partial, okay? And that partial is very important if property, because it allows us as chemists who make compounds to look for sites that have this polar site that we can attack and do things to it to create new compounds. Okay. And it's all attributed to the electronegativity of the two atoms that are being bonded to each other. If we don't have a polar bond, an unequal sharing, is tough to do anything chemically to a compound to make a new compound. Okay. And that's a true statement at the end. Not much to say about metallic bonding. Metals themselves, they're pure metals are just a sea of electrons, okay? And they just basically, that's why they're very good conductors. And they're also very good conductors of heat. That's about all we're going to talk about with respect to just metals and themselves. Which brings us to the covalent bond, okay? Where this type of bonding is being shared. And there's actual a physical bond occurring. And as I mentioned earlier, there's only three types of bonds. It's either a single bond, a triple bond, a double bond, or a triple bond. And we denote that simply by lines. So this is a single bond. Okay, we just draw a line like that. A double bond, we draw two lines. And a triple bond, we draw, guess what, three lines, okay, to represent elements. So we could have maybe, I'm gonna just generic put an A on each side as far as the elements, A and A, okay? Some examples of covalent compounds are here, carbon dioxide. You have the space fill models here. The black here represents the carbon, and then the two oxygens represented by red, okay? Another example, as I stated earlier, was water. Water is a covalent compound. Here we have oxygen and then the two hydrogens sitting there, okay? Each bond, single bond, has two electrons. Double bond has two lines, 4 electrons. Triple bonds, 3 lines, 6 electrons. Okay? Each line represents 2 electrons. Now, when we compare the single bonds versus the other bonds, we observe that single bonds are the longest and generally the weakest of the bonds. Whereas on the other hand, The triple bonds are the shortest and the strongest. They got a lot of energy involved there. In fact, a single bond, a good example of a single bond would be butane. Butane has a lot of single bonds. And we all know about butane, you know, flick your Bic on your lighter. Okay, also propane is another one, single bond, methane, so forth. Anyway, those are single bonds, very weak. Acetylene, for example, is a triple bond, and it is very, very powerful. I don't know if you ever use one, but acetylene is in the combination of oxygen, gets hot enough to burn metal. In fact, that's what you use to cut metal. Okay, a lot of energy involved in that bond. It's given off to be used for other things like burning, cutting metal. Okay, difficult to cut metal with butane or propane. You don't have that much energy. No. Okay. Now, it was thought with respect to covalent bonds that it would be analogous to ionic bonds in that they just come together and don't actually touch anything, or just touch each other and attract each other, but as far as they go. Now, if you look at this particular compound, which is HCl, which would be hydrochloric, hydrogen chloride, I should say, because it's gas in the state. So to make HCl, it was thought that if you take the radius of the hydrogen atom and the radius of the chlorine atom, which are given as follows, the hydrogen atom 0.037 nanometers, that's 10 to the negative 9 meters. And the chlorine atom has one of 0.099 nanometers. When you make a bond between those two, that the bond will be the sum of each particular radius, like so, okay? That is what was being thought. So 0.037 versus 0.099 would give you 0.0136. That is what was being expected, but that is not what was found. Instead, they found that the bond angle for HCl was 0.127 nanometers, much smaller than the 0.136. That's attributed to the fact that in this particular bond, which the diagram is kind of over exaggerated, but to show you that this area here is the overlap, where some of the hydrogen overlaps with the electrons of the chloride, okay? And hence that bond angle gets smaller. Right? That is what the covalent bond is doing, because my fingers represent two electrons again to come one in each atom to make a bond. What is thought to be, what was thought to just occur with my fingertips representing a bond, what actually occurred, there was overlap between the two, okay? And there's a sharing of electrons between the hydrogen and the chloride. Right now, we're just going to say sharing, but we're going to learn that in this scenario, it was unequal sharing. And because it's unequal sharing, it created a dipole, two poles in that bond. Okay? All right, so this kind of break and for a little bit and talk about energy. Okay. Energy is required to break or form a bond. So if you want a chemical, you want to create something, you got to put some type of energy into that bond to break it, so it allows you to create other things. So to break or form a bond, energy is created, okay? And when we break bonds, it always requires energy. It makes sense. I got to break something up. I got to put energy into the system. That being the case, what that means is that energy is absorbed by that system, okay? And absorbing that energy classifies that reaction as an endothermic reaction, endothermic process. And it literally gets cold, okay? A good example of this, going to pharmacy, buying a cold pack. If you buy that cold pack, instructions are to take it and break the inside so the chemicals can mix. And when they do that, it gets cold. That's because what's happening with those chemicals is an endothermic process. Okay, bonds are breaking in there. All right. So what that means is that energy is a reactant. So here's our reaction. Okay, here's our arrow. And to the left, the arrow are our reactants. And we got to put energy, heat into the system to break up HCl into the respective atoms. Okay, energy is a reactant. Forming bonds always releases energy, okay, which results in what is called an exothermic process. It gets warm. Endothermic is cold. Energy goes into the system. Exothermic, it's hot. Energy is given off to the system. Okay? And in this case, energy is a product. Notice in the first example, heat was to the left of the arrow. Now it is to the right of the arrow. A good example of this would be, again, back to the pharmacy and ask to purchase a hot pack. You can buy these where you take these packets, smack them up, and the chemicals in there mixed give off heat, okay? And it gets hot, and you put them on your shoulder or wherever you hurt your muscle, wherever you need it. So exothermic versus endothermic processes. True or false? Question here says, electrons are shared in this structure. Now, you may not know what compound, you may not know what H2S is. That's okay. But I hope you can identify that you're dealing with hydrogen and sulfur. Once you realize that, you ask, okay, am I dealing with ionic or covalent? And in this case, we are dealing with a covalent system. So now you can answer the question, are electrons shared in this particular compound? And the answer would be yes, because it is a covalent compound. And it's covalent because there are two nonmetals interacting in this particular compound. Yeah. That'd be true. The bond between hydrogen and sulfur is ionic. That's totally false, right? Because hydrogen's a nonmetal and sulfur is a nonmetal. So that is totally false. And then the bond length, the HF bond length is less than the sum of the two atomic radii, and that is true. Remember that diagram? We thought that there's an overlap when two of the atoms come together, so that radius, bond length is less than expected. And then breaking the HS bond releases energy, and that is a false statement, okay? All right. Well, I tell you what. Let's take a quick short break. Okay, and let us get into what we call Lewis dot structures, and this is the beginning of working with elements, which allows us to make structures, make compounds. Okay. So let's take about a 10-minute break. I got 5:44. Excuse me. I need a break. Let's come back at 10:54. Okay. Hey. Uh-oh, looks like I lost one. All right, Isaiah, you got a private discussion on Lewis dot structures.
Right on.
All right. Okay, so Lewis dot structures. When it comes to atoms, we're going to do atoms first, and then we'll get to the molecules. And the atoms is a piece of cake, because all you got to know is how many valence electrons it has. So that means that you only need to worry about looking at group 1A through 8A, because we don't know when it comes to the other elements. Okay, so only for the A elements. So we know the group number gives a number of valence electrons, and we simply put the symbol of the element down, and then think of the element. Let's just say it's an arbitrary A element. Think of it as a box around that, okay? And now we're going to put electrons around that symbol. That box won't be there, but we start on one side of the box. Which side you start makes no difference. Let's say it's hydrogen. Well, hydrogen only has one valence electron, so we just simply put a dot to represent one hydrogen, one electron, valence electrons. We go across to helium, the periodic table. Well, it has two valence electrons, so we just go through it the other side and put it on the other side. We don't put it on the same side, meaning, this box here, put 2 here, because we got to fill them up sequentially. We fill up the s orbit. That electron goes in one way, and then we do the second one. That electron goes a different way, and this represents them going the same direction, but they're in different directions. So once we get there, we go around to the other, around the product table, get the lithium. That's got 3 hydrogens. We just put the dot right here. Carbon has 4. We go around there. And then we continue, and now we can start doubling up, okay? And we keep adding them and go around the horn, so to speak, until finally we're at the noble gas. We got 8 electrons all the way around whatever noble gas that was, okay? So that's all we got to do to it. Nothing fancy. Just keep them sequentially filled around the symbol. Okay, so here asking you to do the Lewis dot structure for the atoms: potassium, oxygen, silicon, magnesium, and iodine. But to do that, we go find each one, find out what group it's in. Okay, that tells us how many valence electrons. And then that aspect about learning how many valence electrons is important. It's very important, because we're going to eventually get to the point where we're going to have compounds. Compounds are more than 2 different elements. And we're going to have to start counting the number of valence electrons. So when a compound comes together, it brings along its valence electrons, and then get put together in such a manner that what we got to do is to count the total number of valence electrons that all the atoms brought through the structure. And that then tells us how many bonds we need to make, okay? And now, once we know the total number of valence electrons, that's the number we work with. We can't change it. We can't add any more or subtract any more. We got to make that work. More on that here in a second. But here's the Lewis dot structures. For the atoms, potassium group 1, you can see just one dot. Where you put it, on which quadrant you put it, as if this was a box, it makes no difference, okay? Top, bottom, left, right. Okay, so on down to 4. Silicon, just like carbon, has 4 electrons, because it's in group 4, just like carbon. 4 valence electrons. So those are the Lewis dot structures, pretty straightforward. Okay. Lewis dot structures for atoms. When we talk about compounds, what we got to do is a stepwise process. Step one, we add up. Well, first of all, you'll be given a formula, and you'll be told who is the central atom. And so if, as the example I used earlier, where I gave, let's say, carbon and 4 hydrogens, normally what's underscored or underlined is the central atom. So that tells you carbon is a central atom. And that means whatever follows is bonded to the central atom, okay? Another aspect to remember that hydrogens always make one bond only, one bond designated by one line, okay? They can't make double bonds, can't make triple bonds. They only can make one bond because its duet, its rule is a duet, okay? Now, when we start looking at the bonded structure, let's say we continue with methane, we eventually get to this where we got 4 bonds, okay? We can, each line represents 2 electrons. So in here, that line represents 2 electrons. Those 2 electrons are being shared with the carbon and the hydrogen, okay? This also has 2 electrons that are being shared with the carbon and the hydrogen. And of course, this one here, and of course, the last one here. Each line represents 2 electrons. So we can count that pair to count towards the carbon and the hydrogen. So the hydrogen has a duet rule. There's 2 electrons around hydrogen. Hydrogen's good. The carbon requires 8. We got 4 lines around carbon. Each one contains 2 electrons. It has 8 electrons around it. The octet has been fulfilled. Okay. The point being, when it's bonded, you can count those electrons to either to both whatever is bonded with that single bond. Okay, whichever atom. Okay, so we tally up all of the number of valence electrons, and then we surround the central atom with the other atoms and just draw a single line, because we know we got the central atom and everything else that follows is bonded to the central atom. So in that example where we did HCH4, we see here that carbon is the central atom, and these 4 hydrogens are bonded to the central atom. So we can very quickly draw this formula right here. Okay? Because we have 4 items around the central atom. Right. Then we check to make sure that the octet is fulfilled around all the atoms, except for hydrogen, which is a duet, and that I just showed you earlier. Hydrogen can only make 1 bond. That's the thing to remember. 1 bond only for hydrogen. Okay. All the other ones, you got to have a combination of 4 bonds. Combination meaning, for example, is this. It could be 4, let's take carbon, for example. There's 4 bonds around carbon there, okay? It could be a double bond and then 2 single bonds, okay? Or it could be a triple bond and 1 single bond. So any combination thereof to make sure that the octet has been fulfilled around the central atom. If in this case, carbon was the central atom. And for that matter, for any atom that's involved in writing the structures, the octet has to be fulfilled. Then we do a final check, and we make sure that the valence shells that we calculated, the valence electrons that we have, what we calculated, remains the same, because it's quite easy to lose a pair of electrons. You know, some people like to use the dots, and that's fine. Let's go back to that methane. Some people like to use the 2 dots, like so, to depict, and that's okay. You can do that. Or I prefer the line simply because it's just easier. You very quickly draw a line, you're done. I don't have to keep track of anything else. Double dots, you know, you can lose a dot somewhere along the line. But what is meant for number 4, final check, is you go back to your structure that you come up with and you count all of the valence electrons that you calculated to have. Okay, if you calculate 10 valence electrons, then when you're done, you need to have 10 valence electrons. Okay, like I said, you can't add, you can't remove. You got to work with what you're given. Sometimes it looks like you don't have enough electrons. Okay, that's okay. Okay, because the structure of that compound could be it in that it has a double bond or even a triple bond. So what you do is you start taking electrons from one atom and share it with the other atom that is short electrons, and you start creating double bonds and necessary triple bonds. And that's how far you can go. You can either make double or triple bonds. Okay. Now, once you got the structure put together, you identify your bonding pair and your lone pair. Now, what do I mean by that? Well, let me clear this up. Let's say we're going to do water, but water ends up with this kind of a structure. Okay. So what this means is this: there are two bonding pair. Those two pairs of electrons bonding electrons are bonded. Now, oxygen and hydrogen are bonded. There's two of those bonds. There's also on the central atom what we call lone pair. They are not bonded, okay? They are not bonded. They're sitting on the central atom to maintain the octet, because those are the valence electrons that we have. And that's the only place where they could be in this example, because they can't be in the hydrogen, because the hydrogen's already happy, if you will. It's got two electrons around it. I can't add two more on top of it. Okay, it doesn't have the capacity hydrogen does. So those two electrons have to go in the central atom. And there are 8 around them. 4 of them, 8 pair. 4 of them are, or 2 pair, are non-lone pair, and the other 2 pair are bonded pair. What that means now, once you identify that, you put it into the general formula format. In this case, we always have an A. B is represented by 2 because there's 2 hydrogens in the central atom. And then we have E2 because E's represent the lone pair of electrons on the central atom. In this case, there's 2 of them. So it's a subscript 2. We take this general formula and we go to the shapes table, okay? From the shapes table, we look for A, B2, E2, and guess what? There it is, right here, A, B2, E2. Its geometry is given as follows, right there in the next column. And the name of that geometry is called bent. And that bond angle is much less than 109.5, okay? So that is the 3-dimensional structure of water using this technique. Okay. All right. Well, let's do an example. We got H2O. Okay. So oxygen there's only one oxygen. Okay. If we look that up, we have a total of 6 valence electrons. Okay. And then we have 2 in hydrogen. 2 hydrogens, each one brings 1 valence electron, so it's a total of 2. So we have a total of 8 valence electrons. Now what I do is I divide it by 2. That tells me that I got 4 pair to work with. I use pair because it's a lot easier to keep track of pairs than it is to keep track of individual dots. Right now, 8 dots is not too much, but you can have like 32 dots. You know, so I just divide by 2 and that gives me pair, and I can just count the lines, okay? The central atom is given to you, and that is oxygen. So we can very quickly write down the central atom, which is oxygen, and I have 2 hydrogens, so I can very quickly bond 2 hydrogens, okay? Well, that takes care of 2 pair, right? So I got 2 pair left to work with. I got to put them someplace. I can't put them on the hydrogen because hydrogen's happy now with this duet. So the only logical place to put them is on the central atom, which is the hydrogen. Okay, and I can put dots there or I can put lines. I can do it like as follows. That's fine doing that. Two lines like that. Either one works best, whatever works best for you. Okay, then I go back and I check. Do I still have 4 pair? Well, sure enough, I got 1, 2, 3, and 4. So that means I'm good. I still have the 4 pair I calculated with. That is my formula. Then, as I stated earlier, next step is to determine the general formula, which we just did earlier, and we ended up with this. This sends us to the shape table, okay, which then gives us the geometry and the name of that geometry and the bond angle for that compound. Okay. So we add up the valence electrons, okay. We put the central atom down, and then we draw the 2 lines for the 2 atoms. And then, as I stated, we have 2 pair left, so we can't put them on the hydrogen, okay? So they must go on the oxygen. And so we put them on there. Oh, I forgot to identify the lone pair and the pair. So this example has 2 bonded pair and 2 lone pair. And then we went to go back to check to make sure that we still had 8 valence electrons or 4 pair. Okay, they use 8, but don't forget, you can deal with this and pair. And I like I said, I like to work with pair. Now, not only that, the number you come up with should always be divisible by 4. So you come up with 9, then something went wrong, okay? So that's also a good check, dividing by 2 to see if you got enough electrons. The other aspect too, and we're going to do examples where you do double and triple bonds. If you can divide by a number and get, let's say you inadvertently divided by, you had 6 and you got 3 pair. Okay, just for argument's sake, let's say you calculated 6 pair and you divide it by 2 and you say, I got 3 pair to work with. Well, you give it some thought. Okay, 3 pair. Well, that means that obviously I can put the 2 hydrogens together. That takes care of 2 pair. I got 1 pair left. Well, I put it here and I'm like, wait a minute, that's not going to work. I did something wrong here because at the most I got 6 electrons around oxygen, okay, based on my calculation here. So that's a flag to tell you, I need to go back and check and make sure I use the right number of valence electrons. Okay. All right. And that's the structure. All right, well, let's do a couple of them. So here's this compound, which is HCN. Yes, I know you may not know what they are. That's okay. But you're given, you see it's underscore, you're given the formula. You're given the structure or the formula. 1 hydrogen, 1 carbon, 1 nitrogen. All right. So what we do is we find out how many valence electrons we have to work with. We got 1 of each. Okay. So we got 1 valence electron for the hydrogen and 4 from the carbon, and then we now have 5 from the nitrogen. Okay. So that's a total of 10 valence electrons, or 5 pair to work with. Okay. And that's your number, 5 pair. I gotta have 5 pair when I'm done. All right. So we're given that carbon is a central atom. So we put carbon in the middle, and then you can see that just the way they drew it, looks like we got 1 hydrogen and 1 nitrogen. Okay, we're done with that. That took care of 2 pair. Did it not? 2 pair. So we got 3 pair left over from the original 5. So where you put it makes no difference. Obviously, you can't put those 3 pair on the hydrogen. Hydrogen's happy now, okay? What I tend to do, it's easier for me, check, depends on you, any how you want to do it. I always start from the outside atoms, and if they're not, don't have enough, I put them there first. Then I work my way in after if I got extra, okay? So I'm gonna put 3 very quickly, and I'm gonna put them on the nitrogen, and I'm gonna use 3 lines. So I got 1, 2, and 3. All right, now I count the number, and I took care of my 3, so I'm done. That checks out. This is supposed to be 5 pair. That's how much we start off with. So I count. I make sure I've not lost anything. 1, 2, 3, 4, 5. I still got 5 pair. It very easily you can lose one of these lines in the whole process. So after each step, do an inventory to make sure you got the correct numbers of what you calculated. All right, now we check the octet. If you look around nitrogen, there are 8 electrons. 3 of them are not bonded. One of them is shared with a carbon. All right, so nitrogen is okay. If you look at hydrogen, it's got 1 bond to carbon. That's okay. You look at carbon, you can see that there's only 2 bonds to carbon, 1 from the nitrogen, 1 from the hydrogen. That's a total of 4 electrons. Not enough, okay? So what we do, we say we borrow from Peter to share with Paul. All right, because Paul here has a lot of electrons, or Peter, which I'm going to call, got extra ones. So I can take this, one of these, and I'm just going to draw a line here to tell me, make a double bond. So now I go C, double bond, and then I keep those other ones there, and I get my hydrogen, okay? Now I check the octet. Nitrogen's still good, okay? Nitrogen still has 8 around it. 2 of them are not bonded, and 2 of them are shared with the carbon. Carbon now has 3 lines, 3 bonds around it. That's a total of 6, so it's not working yet. So what we do, we continue in making another bond, this time a triple bond, and you just take that one, I put an arrow there, so now I got carbon, triple bond, nitrogen, lone pair, and hydrogen. All right, now go back and check and make sure you still have 5 pair from the original. I got, 1, 2, 3, 4, 5. 5 pair, I'm still good to go, okay? Now check the octet. Make sure that everybody has 8 electrons or 2 electrons of this hydrogen. Hydrogen's good, okay? Carbon, well, there's 1 pair shared with the hydrogen, and there are 3 pairs, a triple bond shared with the nitrogen. So I got 8 electrons around carbon, and carbon is okay. Nitrogen has 1 lone pair on itself, plus 3 that are shared with carbon. So that's a total of 8. So nitrogen's happy. So our general formula is as follows. Our formula is H single bond carbon, triple bond nitrogen, okay? General formula. A is our central atom, which is carbon, and B represents the atoms bonded to the central atom here, which is 2 of them. Remember, they don't have to be the same. We got 1 nitrogen and 1 hydrogen. So our general formula is AB2. You go to the shapes table and you look for AB2. And it is the very first one. Remember, we got this. Okay. And we had AB2. So here's AB2. There's a geometry. It is called linear. Okay. And it has a bond angle of 180 degrees. That's one. And there you go. Notice I use a line for the lone pair on nitrogen, but you can use the double dots like the diagram. Okay. All right. Let's take a look at this guy. We have one carbon, one hydrogen, 3 fluorides. All right. Therefore, valence electrons, we got 4 from carbon, 1 from hydrogen, and fluorine is in group 7, and there's 3 of them. Okay, so isn't that 21? Okay. Tally it up. We got 4, 5, 6, 26 valence electrons or 13 pair. Okay. Carbon is the central atom. So now we can put carbon, and we have 1 hydrogen and 3 fluorides. So we can very quickly put 1 hydrogen with a bond, 1 fluoride, 1 fluoride, 1 fluoride. Okay. That takes care of 4 bonds. So that leaves, well, 4 pair. That leaves 9 pair. Okay. Now take a look at this. I got 9 pair to put someplace. I cannot put it in the central atom. Why? Because carbon in the central atom is already happy. It's got 8. I cannot put it in hydrogen because it has a duet. So I can't put it there. So the only place it can go on would be on the fluorides. So starting outside in, put in, I'm going to put 9 lines. You got 1, 2, 3, 4, 5, 6, 7, 8, and 9. 10, 11, 12, 13. So that's a double check. I got 13 lines, 13 bonds. Okay. My central atom is A, always will be A, and B is 4. Doesn't make a difference if they're the same or different. I got 3 hydrogens and 3 fluorides and 1 hydrogen. That's a total of 4. So that is our central atom. Okay. That means that we go to the shapes table, look for AB4, and sure enough, here we go. AB4, tetrahedral, it's the most common one. Tetrahedral, its bond angle is 109.5. Okay, and that is for HCF4. Okay. There you go. All right, carbon dioxide. Next one up. Now, this is important to come up with the right structure, because with this information, now we can look at the whole molecule and determine whether that whole molecule is, remember the term polar and nonpolar. Nonpolar is more oil-like, polar is more water-like, okay? All right, so far we got 2 polar compounds, and we'll learn how to distinguish that here in a bit, because then that tells us what type of forces are involved for that particular compound. Right, carbon dioxide. Well, you get carbon, 1 carbon and 2 oxygens, so we got a total of 4. Excuse me, and 12 for oxygen. I had a senior moment there for a second. I was thinking it was 5. No, that's nitrogen. All right, so we got total of 12. There's 2 oxygen, that's 12. So we got a total of 16, right? Or 8 pair to work with. That's my maximum. I can't go any further. Carbon is underlined, so we got carbon is a central atom, and the 2 oxygens are bonded to the central atom. Well, after that, You got two oxygens, yeah. Let's stick with these 12. Okay, 1, 2, that takes care of 2. I got 6 paired left, right? So where I put them, I can put them here, I can put them anywhere. But I like to go starting from the outside atoms and then work my way in. So I got 1, 2, 3, 4, 5, and 6. Then the 2 inside, that's 8. So that corresponds with the original 8 pair that I'm started off to work with. Okay, now you check the octet. If you notice that the oxygens are both have 8 electrons around it, okay? So they're happy, but the carbon only has 4. And so like I stated before, you can take from Peter to share with Paul. And in this case, I'm going to do that and from both directions. I'm going to take 1 pair from this oxygen on the right side and take 1 pair from this oxygen on the left side. And then I'm going to make a double bond between. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8. I still have 8 electrons pair. So I'm good to go. I got a carbon with 2 double bonds on each side. And then I got 2 lone pairs on each oxygen. Our general formula will be AB2. And that'll be linear. You can look that up. That's a general formula AB2. There are no lone pair on carbon. Okay. There are 8 electrons, so that's good to go. All right. So you come up with that. Now, we're going to learn that this molecule, carbon dioxide, that even though it has polar bonds, it is nonpolar. Okay, because the polarity cancels out, and we'll get to that in a second. But do recognize that between the carbon and oxygen, they had 2 different electronegativities. The oxygen is more electronegative than the carbon, which means that the oxygen is pulling the carbon onto itself much stronger than the carbon is. And we can draw an arrow to represent that pull, meaning that it's taking electron density away from the carbon direction and it's pulling it toward the oxygen. And it's going in both directions like that, which is very significant because that effect gets canceled out. But more on that at a later date. Definitely we'll be coming back to this. Oh, all right. So you saw the formula, but let's work it through. We have nitrogen, which is 5 valence electrons, and then 3 from the hydrogens. That's from nitrogen and hydrogen. That's 8 divided by 2. We got 4 pair. 4 pair. Nitrogen's the central atom. And then 3 hydrogens bonded. We can very quickly write that down. Okay. That takes care of 3 pair. We got 1 pair left. Well, that 1 pair cannot go on hydrogens, obviously, for the reason we talked about. And the only place they can go logically is in the central atom. Okay. And so now we count the electrons. We still have 4 pair. We got 3 of them bonded to the hydrogen, and then 1 pair that is on the central atom. So the general formula would be A, B, 3, E. This is where E is, because E is a number of lone pair in the central atom, and so it's AB3E. And that is a general formula for this species. And I'll give you the name of that here in a bit. We go to the shapes table, look for AB3E, and there it is. Trigonopyramid right here. Okay. That bond angle is less than 109.5. And it's less because what's happening here, these lone pairs take up space, so they're shoving those bonded pair down. And so that bond angle gets less. The same is happening right here. Okay. And it's really happening right here because of those lone pair on the central atom. And there is that formula with the lone pair. Yeah, we'll come back with more examples at a later date. And we did HCN. Basically, this is a rehash of what I just went through. Here's the formula. We add up the valence electrons from every atom. One from carbon, one from hydrogen, 4 from carbon, 5 from nitrogen. So we have a total of 5 pair, okay? And we go ahead and write it with carbon bonded to nitrogen and hydrogen, leaving us 3 pair left. And then we have to just share those 3 pair or put them around the 3, the remaining 2 elements, not remaining, but the carbon or the nitrogen. I chose to put them around the outmost atom, which is the nitrogen. And then we start making double bonds as needed and triple bonds as needed. We ended up with that structure. Okay. All right. Well, I'll tell you what. Let's stop it here. Okay, we're about halfway done. This continues with polyatomic ions. What those are? Yeah. This is slide done. Seven and then 21. What these polyatomic ions are is if you go to the periodic table and you go down here to the bottom left. Okay. And they're given here. We're going to be using these polyatomic ions quite a bit. But these polyatomic ions are coming units. And if we need more than one, I kind of introduced it way back when where we put parentheses around it. We don't separate them. They have their own structure, even have their own name. We don't change the name. So ammonia is ammonium, acetate, then hydroxide, cyanide, etc. That's what their name is, okay? We don't change them. But we need to kind of apply what we just learned about the Lewis dot structures for neutral compounds, had no charge, and apply that to these polyatomic ions that do have a charge. And everything's the same. The whole process is the same with 2 exceptions, okay? Depending if that polyatomic ion is positive or negative, we're going to add a number for that charge. If we have a positive, we're going to add electrons. If we have a negative, we're going to take electrons away, okay? In the number wise only. You're not really taking them away, you're adding a value because those electrons are being tied up. Those are the positive cations. Those electrons are there, but they're being tied up by being bonded to something which gives them a plus charge, okay? All right, so it's negative, we add, I said that backwards, sorry, and positive, we subtract. But let's stop it here and we'll go through some examples of that and finish up this chapter next Friday, okay? So right now you were done with chapters 4, 5, and 6. That should help you out. You got a week for the exam next Friday, which will open up, I believe, at 7 or 8, 7, I believe, and end at 11 p.m. So don't forget about that. All right, Isaiah, you have any questions?
Not at the moment. I mean, I did earlier, but I can't remember off the top of my head. But I'll email you.
All right.
it's mainly about what you just went over with chapter
Okay.
7, writing out the formulas and compounds. So,
Okay.
but when they pop up, I'll email you.
Okay, sounds good. Well, also next week, we're gonna be finishing this up. There'll be maybe some more examples that might help
Okay.
when we go through them. So either way, email me or with whatever works best for you. Okay,
All right. All right. Thank you, sir. I appreciate
thank
it.
you. All right, have a good, safe weekend.
Same to you.